Okay, good morning, everyone. Welcome to the second day of this conference, and let's start. Our first speaker for today is Daniele Oriti from Ludwig Maximilians Universität in Munich, and is going to speak about cosmology as quantum gravity, hydrodynamics, and hydrodynamics as cosmology. Thank you, David.
Yeah, thank you. Can you hear me okay? Yep, good. Okay, so let me start. I decided to put the main messages on the very first slide so that you can keep them already in focus. And I will in fact repeat each of them in the corresponding session in each slide. That's the only thing you have to remember at the end of the talk. All the rest is because I have to fill 1 hour. There will be some technical parts for the mathematics fetish in the group, but I'll try to stress the main point, the main conceptual point again, whenever needed, because that's, again, the only thing you really need to keep track of. The rest I can give you more details in person, and I can fill you up with more mathematics or physics if needed. So the one main message is that we now can derive in certain formalism for quantum gravity an effective cosmological dynamics, which is a big deal because in many of these approaches, the gap between the fundamental description and any effective gravitational description was in fact the key issue. But the real point I'm going to stress is that the way this effective gravitational and specifically cosmological dynamics is extracted is from the effective hydrodynamic description of the underlying microscopic dynamics. And it takes the form of a hydrodynamic-like equation, not on a manifold, on a space-time manifold, as usual gravitational physics is formulated, but on superspace, the space of field values, the space of fields, which is a manifold in itself, but is not the one we normally define fields on. In order to set the ground for why this type of description is reasonable, and in fact something we should have expected, I will have some preliminary discussion on one particular view of symmetries, about symmetries in general relativity and what they tell us about the physical or unphysical, in this case, role of the manifold, the space-time manifold on which we define fields. And the main message there will be that, in fact, gravitational dynamics at the classical and continuum level should in fact be best understood as dynamics on superspace, on the space of fields. Once I've given this two main messages, which is the core of the talk, I will in fact show that we are aware, we know from the literature in mathematical physics about other maps from hydrodynamic equations, standard hydrodynamics for realistic fluids defined on a usual space-time manifold, maps from these dynamical equations to relativistic cosmological dynamics of the general relativistic type. And if it was not for the first two parts, you could take that just as a mathematical fact with no particular significance. And I will try to argue that we can now reinterpret those results as having a greater potential physical significance for quantum gravity and for our understanding of gravitational physics. And then we'll conclude. Let's see if it works. So it works. Fantastic. So I can move up to here. Okay, and I will close with some more speculation in addition to what quantum gravity represents on a standard day, on the average day, which is with the suggestion that maybe if we change the perspective and we take on board the previous 3 lessons, then there is hope for reproducing gravitational dynamics in the lab in the context of analog gravity models. And that is normally considered a no-go. I mean, you can do a lot of things in analog gravity, but not reproduce the gravitational dynamics. And I will explain why I think that there is, in fact, hope. Okay, so let's start. I start with the standard relativistic gravitational physics, GR, continuum classical. The message again is that you should understand it as dynamics on superspace, on the space of fields. And the reason for that is that the diffeomorphism invariance, the symmetry of general relativity, implies that superspace is in fact the correct domain for physics, and that physics is in the relation among field values rather than the value of fields at a given point in a manifold. So our model of the world in classical relativistic physics is given by some 4-dimensional, regardless of what string theories say, 4-dimensional smooth manifold, and with a Lorentzian metric, plus additional tensorial fields, scalars, vectors, and so on. Then we have maps, the diffeomorphisms, that are maps between points on the manifold, and that induce maps between tensors, between the fields we put on the manifold. Leading from a given tensor, which takes certain value at a given point on the manifold, to a new tensor at a different point in the manifold, which in fact will take a different value at the previous point. Now, there is a long history of debate and work about what are the implications. I'll cut through that and just proceed by saying that the fact that we have diffeomorphism invariance for the equations for general relativity, which map solutions to solutions, even if they correspond to different values at the same manifold points, it has to be taken to imply that the manifold itself, its points, the directions on the manifold, the associated coordinate systems, of course, are unphysical. That is, that if we want to be a little bit more careful with what plays the role of space-time quantities and space-time in our model, is not the manifold. Events are not manifold points. Time is not a time-like direction on the manifold. Space is not the set of space-like directions on the manifold. Now, knowing about different invariance, this sounds reasonable, but of course it goes against what we normally do when we do general relativity. We routinely use points on the manifold to identify events and so on. We'll clarify in a second in what sense that is correct, but it should be understood as the result of a particular idealized description of what we actually do and what a more realistic modeling should be. So the other implication is that fields themselves are unphysical objects if you understand them as functions on manifold points. The fact that you have a certain value for a certain field at a particular point in a manifold is not in itself physically significant, because the point itself is not physically significant. So what should be a physical notion of event? Space and time will have to be defined in terms of different variant observables, and they should be constructed using the fields, but in a different variant manner. And I will mention a strategy to do that. None of what I said has to do in any way with coordinates. It has nothing to do with using or giving significance or not to coordinates. Any theory, no matter what the symmetries are, can be written in a coordinate-independent manner. However, all this is nice words to some level, but we do not know of any formulation of general relativity that is purely in terms of different variant quantities. You have to reconstruct those quantities through some painful procedure. What is one procedure to do that? which I'm going to rely on in the following, is a so-called relational strategy. It means that what localization in space and time is relational. That is, relational observables to which we assign a spatio-temporal meaning are actually functions of appropriately chosen reference fields, not coordinate frames, but reference fields. Because they are functions of reference fields, they are in fact, from a more mathematical perspective, correlations on superspace, correlations on the space of fields. What does that mean in practice? That we have to identify in this strategy some of the dynamical fields in the theory, say 4 scalar fields, and we identify them as providing us a definition of time and space, meaning that we use them as clock and rods, and then we use their values to label the evolution or localization in space of the other fields. So that the evolution in time is really the evolution of certain fields as a function of another field that we used as a clock. We picked up as defining our time. The same is for localization in space. Now, what is the usual, where does the usual language in terms of coordinate frames come in? Well, it comes in the moment we idealize our physical fields that we picked up to define clock and rods to be particularly nice. We neglected their back reaction on the geometry. We neglect the fact that they have their own self-interaction in general. If they are quantum, we neglect the fact that they have quantum properties and so on. In this particular approximation, which is a very idealized situation, so the situation in which they behave like test fields, then they in practice behave like a coordinate frame. And there you recover the usual description of the metric in a given coordinate frame, and you interpret that as corresponding to a given observer. So in GR, the physics should be found in the relation between dynamical fields, which are, again, as I said, correlations on superspace, on the space of fields. Let me give you a much simpler example to get the idea. The parametrized pendulum. I mean, you know what a pendulum does. It's a very simple mechanical system. The only thing you actually measure is the position at a given time. That's the only dynamical variable for which you have an equation. Just 1 degree of freedom. There is a general solution, and then initial conditions will tell you which specific solution you have to pick up. I said you only have one quantity you actually measure, the position at a given time, which means that in fact you have 2 quantities you have to measure, the position of the pendulum and time. You have 2 quantities that lead you to predict one quantity, which is one as a function of the other. That's the thing that the theory gives you as a prediction. So Q and T, the position and time, can be measured. They are what Rovelli calls partial observables. But the theory can only predict as meaningful one quantity, which is Q as a function of T, which is called the complete observable or a relational observable. Now, this should be uncontroversial, but you should still on the physical ground. But what does that have to do with GR? Well, let's parameterize the pendulum and we introduce a symmetry, which is in fact a one-dimensional diffeomorphism symmetry. Now, forget about the equations. The idea is simply to treat Q, which was one partial observable, as a field over some auxiliary mathematical structure, which is a one-dimensional manifold of some parameter tau. And T is also a field over the same manifold, T as a function of tau. So your theory is actually a theory of 2 scalar fields in one dimension. And you know, at the end of the day, the physics should be in the relation between the 2. You added redundant structure. How do you notice that there is a redundant structure? The theory is so formulated as a one-dimensional diffeomorphism symmetry. The freedom to parameterize, reparameterize freely, change the tau variable freely. At the end of the day, there is only one diffeomorphism invariant observable, which is the relational observable we knew already, which is Q as a function of T. That's the only quantity that also in this redundant formulation you can predict that is invariant under the symmetry of the theory. So the point is that GR should be understood in the same sense. Diffeomorphism symmetry tells you that the space-time manifold on which we define our fields is in fact unphysical. We have to define the physics, extract the physics out of appropriate relations between the fields, the field values. So this is the strategy. And an example would be to take 4 scalar fields and write down, I don't know, the Ricci scalar at a point, inverting the notion of point on the manifold with the values of 4 scalar fields, so that you say that you have a certain value for the Ricci scalar when the clock scalar field has a certain value and the 3 rods scalar fields take certain values. That's your point in space-time. That's a diffeom-invariant observable. The point is that GR doesn't come with a natural way of being deparametrized. So there's no set of fields in general that from the mathematical structure you can identify as a preferred physical frame in terms of which express the evolution, the spatial localization of the others. It doesn't work like that. Moreover, there's no obvious reason why if you work with physical frames, the physics should be the same, whichever you choose to express the evolution, the spatial localization of the others. And there are more issues with that, with this description. There are deparametrized formulations of general relativity. People introduce appropriately chosen matter fields to give you a good notion of physical frame and re-express the whole theory in relational terms with respect to them. So we know the strategy can work. And you have to introduce special fields like free scalar matter, pressureless dust. I mean, they're very special type of matter fields that can play the role of an ideal frame in which you manage to deparameterize the whole theory. And this is a very beautiful, but also very useful formulation that has been applied in cosmology and so on. But the main problem is that, to summarize, if the type of matter you have in the theory is physical, is not an idealized frame. If it is an idealized frame and allows this type of deparameterization, it has usually one or more unphysical aspects. So you have to, if you want to be fully realistic, we have to try to go beyond all this. So the main conceptual lesson, and I'm closing now this first part, is that physics doesn't take place on the manifold, on the differentiable manifold of which we define our fields, takes place on the space of fields, on superspace. This is, in the general case, is a highly mathematically complicated structure as a manifold. It's a manifold itself, it has a metric, it has a topology and so on, superspace, but it's complicated. By the way, just a note, it's not just a kinematical statement when I say that physics takes place on superspace. You can even express the full dynamics of GR as the dynamics of a point particle on superspace. This is a well-known fact since many years. So you have also dynamical formulations of the theory that use only superspace. So the practical problem is to obtain this expression of the physics, interesting physics, purely in terms of correlations on superspace, so relations between fields. It's an open issue in general, as I said, but things become much simpler in a cosmological context. there, when we say cosmology, we mean very large scale structures, and it's a good approximation to restrict to global features of the universe, so approximately homogeneous fields. Fields that from the point of view of the manifold, of the space-time manifold, do not really distinguish points in space, in the spatial section of the manifold. So what to work with is not the full superspace, but so-called mini superspace, the space of spatially homogeneous metric and matter fields. It's a much simpler mathematical structure, and you can characterize it's a finite dimensional manifold with a metric, the mini superspace metric, and simple topology and so on. Notice that mini superspace, the space of spatially homogeneous metrics, is in fact isomorphic to the space of metrics and matter fields at a point on the manifold. Okay, so it's like you're only focusing on a single point and you don't care what happens when you look at other points on the manifold. Okay, and here we have a full, it's a very simple theory, generativity reduced to cosmology. Even imposing isotropy, it makes it even simpler. So that's the metric. You get the Friedman-Robertson-Walker metric. This is the flat case. And the only dynamical variables are the scale factor of the universe, basically the volume. And I'm adding a massless scalar field. So the full action reduces to a simple one-dimensional mechanical model. Mini superspace is just a two-dimensional flat manifold with two directions labeled by the scalar field and the scale factor. There is only one relational observable you can construct, which is the volume at a given value of the scalar field used as a time, as a clock. And you have a fully relational evolution for the volume. And there's nothing else to say as far as this mechanical system is concerned. So in this case, you can proceed with the construction of the only relational observable, studying relational evolution in terms of a clock time, and so on. In fact, you can even go to the quantum level. That's quantum cosmology. You can take that system and quantize. This is what also Martin discussed yesterday in a part of his talk. So you can write down states or wave functions on mini superspace, which are functions of the scale factor and the clock scalar field. There is a dynamical equation, which is in fact a constraint. There's no other time variable that can appear there. The manifold has totally disappeared from the description. So it's dynamics on superspace for functions on superspace. Then at the quantum level, the relational geometric observables are constructed as averages. And then you can obtain dynamical equations for such averages, which reduce to the classical one from GR in appropriate limit. Everything happens on superspace, also at the quantum level. So let me summarize this first part. To identify space-time with a manifold and space-time physics with physics on a manifold, meaning the usual differentiable manifold on which we define fields, is at best an approximation of a more fundamental description. And in fact, gravitational physics is relational physics on superspace, on the space of fields. The fundamental formulation of any quantum gravity theory, if it respects diffeomorphism invariance, will not feature a manifold unless you decide to add it because it's mathematically useful for whatever reason, but it will disappear from physical quantities. We don't have such a purely diffeom-invariant formulation of gravitational physics in general, but it's available in simple cases, cosmology being one of them. Such simplified context, I'm going to argue in the following and show you more concretely, corresponds to a highly coarse-grained global approximation of your fundamental theory. So in fact, it corresponds to a hydrodynamic regime of the fundamental theory. So I'll focus on that. Let me start with just some very heuristic picture of what I should expect once I see cosmology as hydrodynamics. So space-time physics in general, and in particular cosmology, as I said, should emerge from coarse-graining of the fundamental description and from the collective dynamics of the fundamental quantum gravity atoms, I mean, fundamental degrees of freedom. And cosmology is the most coarse-grained description, the one where you really focus the global features only. So that's basically what you do in hydrodynamics. So the relevant hydrodynamic observables in quantum gravity, you should expect to be very simple averages of one-body observables. That's what happens in usual hydrodynamics from the point of view of atomic theory or molecular theory. The total volume of space, assuming that each quantum gravity atom contributes a little bit to it, will be exactly such an average quantity. The key hydrodynamic variable should be some sort of reduced density, reduced one-body density. Just like in hydrodynamics, the density of the fluid is the only remaining dynamical variable of the theory once you go to this fully coarse-grained description. And it gives you a probability density for cosmological observables. It should take the form, if all the previous discussion is correct, of a density on mini-superspace, a probability density on quantities which correspond to the variables on mini-superspace. So this is what we expect. We expect on very heuristic general grounds that from quantum gravity, we will obtain an effective coarse-grained, maximally coarse-grained description in terms of some density on mini-superspace. And cosmology should then be extracted from the dynamics of such density. So from the hydrodynamics of this coarse-grained dynamical variable. And it's going to be a nonlinear dynamical equation because, again, it's the result of coarse-graining, just like standard hydrodynamics. So this is the heuristic. Now I realize it a bit in practice. The picture is that quantum gravity hydrodynamics should take the form of a nonlinear version of quantum cosmology, which have a density function on mini-superspace, but satisfying a nonlinear equation. Okay, now I make it a little bit more concrete. From this point for the next 10 minutes, roughly a bit beyond my half, sorry? 33, now 32. Yes, now there will be a few more technical details. And again, I try to, I put them there, but I try to repeat and stress the main conceptual points. So focus on those only. So I work with a specific quantum gravity formalism in which quite literally from the mathematical point of view, the universe is described as a sort of a quantum many-body system. It's called tensorial group field theory and is related to a number of other approaches. So it's not something that just came out of a hat after one difficult night of digestion. So you have a theory in which there are atoms of space, fundamental entities, constituents of space, and they take mathematically the form of quantized tetrahedra. So it's like you chop the space in building blocks, little cells. Then you say, well, each cell, I forget how it's related to all the others in this particular chopping. I look at the data in one of them. It has its own notion of discrete geometry. I can think of edge lengths and volume and areas. This is, of course, very different from any smooth metric field, but for a tetrahedron is enough, and I can quantize that. So people can do that, and we have a Hilbert space for a single tetrahedron, which encodes its quantized discrete geometry. there are a number of constructions. I'll use the notation of one particular, only one of them. So you have a Hilbert space like that, and then there are additional conditions you have to implement, which I'm not going to say more about, in order to have a proper geometric understanding at this discrete single building block level. You can express everything in purely algebraic terms using representations of a group, irreducible representations. For SU2, it's something you may have seen. It's just the representation theory of angular momentum, spins, half integers. And these are the only data you have. You have a discrete structure, a tetrahedron, or if you want, just a node with 4 links, labeled by representation data from SU2, from the rotation group. Okay, so discrete and algebraic formulation. And this data encode, as I said, the discrete geometry of the object. You have a notion of an area operator, a volume operator, an edge length operator, and so on. And then you can take many of them and consider the case in which you glue them to one another. This gluing is basically entanglement across a subset of degrees of freedom. So the connectivity of several tetrahedra to form an extended discrete quantum structure is basically an entangled state of several quantized tetrahedra. I mean, these are just words. In practice, you can actually generalize the construction to several tetrahedra glued to one another. And you can write down, once you have the one body Hilbert space, you can write down a Fock space of many tetrahedra, a priori disconnected to one another. Special states inside that Hilbert space will correspond to connected tetrahedra. But the main point here, and you can generalize in a second quantized language, like in quantum many-body systems with creation and annihilation operators, you can generalize all the observables of the theorem, these discrete geometric observables. In particular, you can consider the total volume of space if space is given by a certain number of quantized tetrahedra, glued or not. Each one contributes a certain quantity, certain chunk of volume, and then you sum, like you would do with the total momentum of a quantum many-body system. Each atom contributes a certain momentum, you take the sum. The key point here that I want to stress is that in such a description, you are far away from any smooth manifold with a metric field and so on. A generic state in such a Hilbert space will not even correspond to a connected simplicial lattice with several tetrahedra connected. Those are only some particular states which have this interpretation. And certainly none of them, I mean, not a generic one, will correspond to a nice discrete geometry. They will have quantum fluctuations, they will have all sorts of pathologies from the point of view of classical geometry, even discrete classical geometry. And even when you have a good discrete geometry, you are far away from a smooth geometry of general relativity. So that's the big gap that one has to fill. So in this sense, at this level of description, the usual notion of space-time has disappeared. You don't have it. Okay, you can also write down a dynamics. You can write down a field theory for such a quantum many-body system. The only thing I'm going to say about this is that you can write down models for such a dynamics. You have to specify a particular action, and then you work with that dynamics. The other thing I'm going to say is that when you expand the theory in perturbation theory, you generate processes for such tetrahedra. These processes take the form of lattices to which you assign transition amplitudes. And here you see the connection to other approaches to quantum gravity, in particular discrete quantum gravity in the usual form. I'm not going to say more about that, but these connections guide your model building. And in fact, you can extend the description in the following sense. I described a single building block to which I can assign geometric quantities, edge lengths, areas, volumes. I can also add the data. How do I do it? I can add those data that when I look at the dynamics of the theory, if I do the coupling properly, the dynamics takes the form of a lattice path integral for gravity coupled to scalar fields, discretized scalar fields. These additional data, which are just real numbers, which I add to the domain of my fields, are then understood as the would-be scalar fields in a continuum approximation. You don't need to know more about that at this stage. So before I add some discrete geometric data only, now I can have an extended formulation in which I have those plus some real numbers, which I interpret as those quantities that will give me continuum scalar fields in some appropriate limit. Now I need to extract that limit. Okay, so if I was God, which is a big responsibility, I would be able to control the full quantum dynamics, compute the partition function, study the critical behavior, identify continuum phases, and do everything that condensed matter physicists want to do, and also they cannot do in simpler systems, let alone quantum gravity many-body system. So you have to resort to approximations and hypotheses. From now on, I follow the hypothesis that the relevant regime for extracting continuum gravitational physics is the hydrodynamic approximation of such a system, and that the proper spatial-temporal or geometric phase in which to do such extraction is a condensate phase. So I'm basically assuming, in words, that the universe, as we know it, is a sort of a quantum fluid, and that its hydrodynamic description is what we normally call general relativity and gravitational physics, appropriately rewritten. So these are two hypotheses, and then that was not supposed to be the case. So this is what I've given already. Anyway, the slides look funny, but the simplest approximation you can do is to approximate the full hydrodynamics, the quantum hydrodynamics, the full quantum effective action of your many-body system with the classical action. It's just a mean field approximation, and from now on, I will just limit myself to that. Two things happen in full generality in such models. First thing, the mean field hydrodynamics takes the form of a nonlinear equation for the condensate wave function. Assuming the universe is like a fluid, it's a condensate, then you have an effective wave function, which is basically your classical field. So you get a nonlinear equation for such function. So your effective hydrodynamic equation is a nonlinear equation for a function over your geometric, discrete geometric data. The cosmological interpretation, however, follows from the next very general fact, which is that the domain of such wave function, which is the space of discrete geometries of a single tetrahedron, if impose appropriate restrictions, is in fact isomorphic to mini-superspace, to the space of continuum homogeneous geometries. So what do you get? You get a nonlinear equation for a function on mini-superspace, on the space of homogeneous geometries. So it's exactly the nonlinear extension of quantum cosmology that I had anticipated earlier. Of course, this is when you give the talks. The way you actually get to things is totally the other way around. So you get an equation, you say, what the heck is this and why is this? Then you understand roughly what it is and you say, I should have understood it before. And you find a lot of good heuristic reasons why that's the best possible result you could have ever obtained. Maybe I should not have said that publicly. Okay, so you can, this was very general. For any model of this, in this class, with this geometry interpretation at the discrete level, these are the general results. You get a nonlinear extension of quantum cosmology as the mean field hydrodynamics, period. Then you have to go concrete, you take specific models and you try to extract a specific effective cosmological dynamics out of them. So we take a model in which we have our discrete quantum geometry plus 5 scalar fields, 5 additional data that have to become scalar fields in the continuum. Why 5? Well, 4 of them give me a physical frame, clock and 3 rods. Otherwise, you have no spatial-temporal interpretation because I cannot construct relational observables that correspond to quantities localized in space and time. I just cannot. There's no such information in the theory, and there shouldn't be. So 4 scalar fields will play that role. A 5th one is basic because you want at least some matter content in your universe, in your emergent universe. Okay, you write down a model with appropriate choice of action with this type of data. Then you go to mean field and you do an extra approximation, an extra assumption, exactly because you want to reconstruct a localized, spatio-temporally localized dynamics. We impose that the condensate wave function peaks well on values of the 4 scalar fields you want to use as a physical frame. In other words, we assume that we are in a particular state of the universe where we have good clock and 3 good rods. Because if they start being wildly fluctuating, well, they can hardly be used as a physical frame. They would not give you a nice evolution picture or spatial localization. The rest is technical details about the states. So this is the point. Then you write down additional assumption. We focus first in the case in which the interactions are subdominant. So they are there, but they contribute less in the free part. Then you assume isotropy, which in practice means that you have a condensate wave function that depends on a single algebraic variable J, this single spin, and your scalar fields. And then we obtain an equation for such condensate wave function. Again, complicated equation with various parameters that depend on the model, on the states, and so on. But in practice, it's a differential equation for the condensate wave function, where the derivatives are with respect to your clock and the value of your clock and the value of your rods. You can rewrite it in standard hydrodynamic form in terms of a density and a phase. And so you can split also in terms of a homogeneous background. So you assume that there is a dominant contribution to your condensate wave function that doesn't depend on the rods. This is your only notion of homogeneity in space. If you have something that depends on the values of your rods, it's not homogeneous. You have a physical notion of a point in space given by the values of your rods. If your function depends on that, it's not homogeneous. If it doesn't, it's homogeneous in a physical sense. It doesn't depend on the value of your rods. So there is a dominant homogeneous contribution, and there is a perturbation, which is instead inhomogeneous. Again, space-time localization is defined in relational terms. You have an equation for the background, and you have an equation for the perturbation. Again, forget about the details of the equation. You keep going with the split. And you focus first on the homogeneous background. Can you extract a homogeneous cosmological dynamics from the equation for the background, for the homogeneous background? It's a dynamical equation for the condensate wave function. It's not yet expressed in terms of any geometric or cosmological quantity. So that's the task. However, you have a number of observables you can write down in the fundamental theory. I give you just one. The total volume of the universe is the volume of each tetrahedron averaged and added for all the tetrahedra in your condensate state. Again, formally, it's like if you were asking what is the total momentum of a quantum many-body system. There is a momentum for each atom, and then you take the corresponding total contribution. Same thing. So you have the same for the value of your clock and rods. You have operators defining the momentum of the matter scalar field. In fact, you have all the observables that you need in a relational description of cosmology, isotropic and homogeneous. You have the volume, you have your scalar fields, which are also homogeneous, and that's it. And you realize that the moment you take these operators in expectation value in your condensate state, which is well picked in terms of clock values and rods values. So you obtain, for example, the volume at a given point in time and space as defined by the values of your clock and rods scalar fields. From this, from the previous general hydrodynamic equation, you can obtain an equation for such expectation values that have a cosmological interpretation. You obtain equations for the volume, for the background, and in fact, you also obtain equation for the perturbations, for the inhomogeneous perturbations. My point in this talk is not to try to convey any pride for all the results you obtain in this formalism, so I just mentioned them very briefly. You can analyze such dynamics for the volume, and you get that at very, very early times, you have a bounce instead of a Big Bang singularity of the same type that Martin discussed yesterday in the first part, so the simple quantum cosmology type situation. At later times, you have a good semi-classical behavior with this is the relational Friedmann evolution in terms of a clock time given by a scalar field. And in fact, you can even show that later, when the interactions become dominant, you have an accelerated expansion, which for appropriate models, it takes the form of a so-called phantom dark energy. Anyway, this is not so important at the moment. You can even do work on the cosmological perturbations. Let me repeat what the lessons we learned in this part, and then I move to the last part. And I have 15 minutes. Good. Okay, so I just list the main lessons, hoping that you notice them, at least some of them in the previous discussion. So space-time and geometry are emergent notions in quantum gravity in this type of formalism from some pre-geometric or non-spatio-temporal, in the usual sense, atoms. So they require a continuum approximation of the collective quantum dynamics. This, I want to stress, is not a classical approximation. It may involve also a classical approximation, but this is a continuum coarse-graining approximation, which has to be done in general at the quantum level. It's conceptually very different from a classical limit of quantum gravity. It's a different type of approximation. The key point is that spatial localization and temporal evolution are relational. So you have to introduce and have appropriate clock and rods. More generally, the universe appears as a quantum gravity condensate, a sort of a quantum fluid. And there is a lot to be said about what notion of emergence you have to apply, in this case, for space and time. Interesting discussion for which I don't have time. The cosmology comes out as the quantum gravity hydrodynamics, as a rewriting in terms of observables of the general hydrodynamic equation of the theory. And it takes the form of a nonlinear extension of quantum cosmology. Once more, as anticipated, the relevant domain of your dynamical variable, in fact, the only domain that appears is mini-superspace. You don't ever introduce a differentiable manifold with fields and so on. It just never appears in the fundamental level and not even at the effective level. If you want to introduce it, you can always do it if it is useful to something, just like we did for the parametrized pendulum. Okay, and I point only without discussing that in all this picture, you see clearly the limits of any effective field theory intuition at a number of points. Anyway, let me move on to the last part. From quantum gravity, you get cosmology as the effective rewriting of hydrodynamics in terms of appropriate averaged observables. In fact, we know a number of other maps at the mathematical level from standard hydrodynamics, non-relativistic hydrodynamics for realistic fluids, and cosmology. I'll mention one and I'll try to convince you that there is a lot more to be found there. A lot more is known and a lot more is to be found. Okay, what I'm going to say in the following will suggest a much broader, still hidden correspondence between hydrodynamics on superspace and GR. And it suggests, in fact, the existence of some sort of physical general covariance, so transformations across physical reference frames. Again, nothing to do with diff fields on a manifold, but really transformations among the physical sets of clock and rods that you can introduce. This is the main message, and as I said, I will repeat it in the following. I'll give you one derivation due to, let's say, 20 years ago. Start from the Gross-Pitaevsky equation, which is a nonlinear Schrödinger equation for a weakly interacting Bose condensate. That's what it is. You have an external potential. You have the self-interaction of your atoms. This is the mean field description of the system. And it's a nonlinear Schrödinger equation because you have a condensate wave function psi, which is function of a effectively two-dimensional space and time. And you have a derivative with respect to your time. We are in space-time, we are in usual physics and no quantum gravity here, yet. This is very difficult to solve in general. You can restrict it to wave functions that only depend on the radial coordinate and time with a special type of trapping potential. Well, you know that the system is fully encoded in the integral moments, which are these average quantities that you obtain from the condensate wave function. This integral moment satisfy a number of relations, which you can combine together into a single equation. Here, trust me, you can do it, just like I trust the author of the paper. Okay, when I checked some of it, but not all of it. Okay, so there is a single equation for these integral moments which contain the physics of the system. Well, then you can in fact now change the page in your book, and instead of finding more hydrodynamics, you find relativistic cosmology. You're a bit surprised at first. You find the Friedmann equation expressed in cosmic time for a scale factor A, and there is a single scalar field phi, for which you have a density, there is some potential here, and the pressure. You change to so-called laboratory time, and you'll see the reason for the name in a second, and then you can recast the same Friedmann equation in terms of exactly the same equation we got earlier, the Ermakov-Pinney equation. In fact, you realize that you have the same equation because you can map cosmological observables, cosmological quantities, the scale factor, the density of your scalar field, the pressure, and so on, to the integral moments of the fluid underlying the same type of equation. Even the conservation equation in Friedmann corresponds to a conservation equation in the fluid. So you map the nonlinear Schrödinger equation and its solutions to Friedmann equation and its solutions by an appropriate map between cosmological quantities and integral moments. It's a mathematical coincidence, you would think. Maybe it is. But this map become immediately, how to put it, natural if you start thinking of this wave function, the condensate wave function, not as living on your usual space and time, but on superspace, the mini superspace of cosmology, identifying the spatial direction with the scale factor and the temporal direction with your scalar field. The moment you do that, these integral moments are just the average quantities that in hydrodynamics you will put in correspondence with these cosmological quantities. You may still think that it's a coincidence, but then there is a larger number of coincidences, but because you can extend this correspondence to anisotropic cosmologies, in fact, also to spherically symmetric black holes, and so on. I give you one other element of the picture. You may still say, well, in cosmology, we have diffeomorphisms. Okay, we took them into account by going relation, and then we don't have any other symmetry there. In hydrodynamics, we do, because if I have a nonlinear equation in flat space, there is my Galilean transformations, translations in space or time, and so on. I have the usual symmetries of non-relativistic physics. In fact, the nonlinear Schrödinger equation has an additional conformal symmetry. Anyway, there are a number of space-time symmetries. Where are they in cosmology? This cannot be the same symmetries, the same systems. Well, it turns out that you can find the same, exactly the same hidden symmetries in cosmology, in the same cosmological system I considered. And they are systems of symmetries, of course, not as transformations on the manifold. You got rid of the manifold already. There you had diffeos and you got rid of them. These are transformations on superspace, on the space of fields, as it should be. If you go back to the previous correspondence here, it should be the case, if the correspondence is to be taken seriously, that transformations of the radial and temporal coordinate in space in the nonlinear Schrödinger equation in standard hydrodynamics should correspond to field transformations on superspace. That is exactly what happens. You can take the Friedman dynamics with a free scalar field to simplify the story. And you find that there is a set of transformations that leave the dynamics invariant. These are symmetries of the theory. Again, forget about the details. The message is the only thing that matters. They, in fact, form a nice algebra. And this is exactly the two-dimensional centrally extended Schrödinger algebra, which is known to be the symmetry of the nonlinear Schrödinger equation. Exactly that. And in fact, it's the same symmetry of this nonlinear Schrödinger dynamics, or the hydrodynamics at mean field of a quantum fluid. Okay. And then I just mentioned that all of this, including the symmetries, have been generalized to several other cases. So it really suggests that there is a lot there to be found. And there is a much more close relation between hydrodynamics, even from the purely mathematical point of view, and cosmology, which becomes a physical relation the moment you understand the hydrodynamic system as defined on superspace. Okay, this is what I already said. I move to the last part, 2 minutes. 2 minutes. The last 2 minutes are the wild speculation, the sort of thing you put in a grant application for some funding agencies. Most of the others will just transfer your application to the trash. But you can be lucky. If really we can map standard hydrodynamics for a quantum fluid, a realistic one, I mean, one that your friends, condensed matter friends, if you have such friends, have in their lab, you know, there's a bucket of liquid helium, And at some level of description, it satisfies an hydrodynamic equation, the Grosspitesky equation I wrote earlier. If you can map that equation to cosmology, you have at least a sector of gravitational dynamics. You don't just have dynamics of, I don't know, perturbations on a given background geometry. You really have the dynamics of the geometry there. So why is this interesting? Because there's a whole field growing, interesting, exciting, and many friends there, which is called analog gravity. And what do they do there? Well, let me give you a brief summary in one slide of the situation of the whole field. Well, one can show that an effective curved geometry, so a curved space-time geometry, emerges naturally and very generically at the hydrodynamic level of description of condensed matter systems. Moreover, there's the interesting part. Excitations over ground states of the same condensed matter system couple to that curved effective geometry and not to the laboratory geometry, which would be flat. So you obtain an effective description of the system as a quantum field theory on a fixed curved spacetime at the hydrodynamic level. Now you can in fact simulate in the condensed matter system in terms of such perturbative treatment a lot of gravitational phenomena, theoretically, and then some of them experimentally. Cosmological phenomena, but even more black hole-like phenomena. And there are a lot of results, including experimental ones. Things that are inaccessible in astrophysics, or in cosmology, or in the physics of black holes, become accessible in such physical simulation. Not a computer simulation, it's really a system that mimics that type of physics. Okay, I don't give you more details there, but there is one big open issue in the whole field, which is that you can reproduce the physics, the dynamics of perturbations over a given curved geometry, say a black hole or a cosmological geometry, but you cannot reproduce the gravitational dynamics, the dynamics of that geometry. In fact, this is the consensus in the community, the analog gravity community, the others don't care, is that the gravitational dynamics just cannot be reproduced. It's just impossible. There's no way. It's a structural limitation of the whole formalism. Why? Well, because the dynamics of that emergent geometry, although it looks like a curved black hole geometry, say, the dynamical equations it satisfies are not the general relativistic equations. They are the hydrodynamic equations of the system. That effective geometry is still a function of the density of the fluid, the velocity of the fluid, and so on, and they don't satisfy a GR equation. Moreover, this effective dynamics, the hydrodynamics that this effective geometry satisfies is non-different invariant, if you want, is background dependent. It comes with preferred frames, and it has special global symmetries. In fact, it has the Schrödinger symmetry that I mentioned earlier. I mean, again, the dynamics is the nonlinear Schrödinger equation. And you don't see any different variance, you don't see general covariance, and so on. So there's no way that dynamics could be mapped to GR. Well, I've just shown you that you can map hydrodynamics to at least some sectors of GR. And conceptually, again, the point is that you should understand that hydrodynamic equation not as defined on a manifold, because the manifold does not appear or should not appear in GR if you were smart enough to write a proper relational formulation. It should be understood as defined on superspace, specifically mini superspace for cosmological applications, in a specific physical frame, a particular set of clock and rods. No, it's not a particular set of coordinates. In the lab, you actually have a clock and rods. And these two dynamical equations share the same symmetry. So there's no issue of a mismatch in symmetries between cosmological dynamics and nonlinear Schrödinger hydrodynamics. And this symmetry is about field transformations on superspace. They are not transformations on a space-time manifold. So in fact, the symmetry exists beyond diffeomorphism. Once you took them into account by gauge fixing, by writing everything relationally, it doesn't matter. Remove diffeos from consideration, remove the manifold from consideration, you still have these field transformations. Okay, so all the results I've shown you give you a proof of principle that this map between general relativistic physics and hydrodynamics is in fact possible, at least in some cases. And then it gives you the quantum gravity fundamental theory background for thinking that it should be possible, and a concrete realization of that in a particular formalism for quantum gravity. So maybe it is possible to have proper gravitational dynamics in quantum many-body system in hydrodynamic approximation, also in the lab, provided we change perspective to a superspace-based one. Thank you.
So thank you, Daniele. The coffee break is now, so yeah, okay, so we started 10 minutes late, so that's gonna be perfect. Okay, so go on.
Thank you very much, Daniele. I won't enter into details with respect to your proposal, not now. But I'm wondering whether you are aware of the debates that are present in the philosophy of science community concerning analog simulations and, let's say, the eventual problems that we find when we rely on this type of models and on the analogical reasoning that is implied therein, and how you address this preoccupation, let's say, or these worries on the philosophy of science community.
Yeah, I'm aware because I have many friends also in that community, and so and I talk to them. My understanding is that the doubts about the validity of the lessons we acquire in analog gravity for actual physics, or gravitational physics, are at two levels. So one is very general, and I leave it to the philosophers. It's whenever you go for analogical thinking, mostly based on mathematical analogy, the formal level of correspondence, how much would you rely on that for drawing physical conclusions? Okay, that's a very good, that's very important debate. I think that it's not specific to analog gravity. I think that is part of a broader issue. You know, we have a mathematical model, and then we have to put it in correspondence with things we observe. How much do you trust what is there in the model and is not in all its elements directly in correspondence with things you measure? I mean, there is the whole issue of mapping, matching models with reality. And okay, I'm not an expert. I'm enthusiastically learning about that, but that's a different story. The more concrete problem with analog gravity has to do, I think, exactly with the main limitation I said. If it is structurally the case that you can only trust the correspondence in terms of the perturbations over a given background, and even worse than that, only those perturbations that do not back-react, because the moment that they back-react on the geometry, you need to use the dynamics of the geometry to study that coupling. If that's the case, indeed, there's such a big limitation that I understand being super doubtful about the validity of the analogy. It bears on my work and my hypothesis exactly because what I'm suggesting is that there is a way to go beyond that structural limitation. It's not a structural limitation, it's a limitation of the way we are using those models. And we can, in fact, simulate, go beyond and simulate also the gravitational dynamics and the back reaction and so on. There will be maybe other approximations, maybe it's valid only in some regime, but then we will be in the usual case in physics in which a particular model applies in a certain approximation, and that's okay.
So we have 6 minutes, and I have one. Sorry, I forgot your name, Michelle, Chris, and then Barbara. So I have to ask you to do the quick version of both the question and the reply, and keep the long one for the break. Albert.
Thank you for the talk. So I want to raise a worry about the relational strategy regarding the cosmological models, because you have these simple models in which you have scale factor, a scalar field, and you say like, oh, we only care about relations about them and so on. But I have the worry that you also have a proper time in these kind of models that you can compute and use these models to say like, oh, the universe lasted for 13 or 14 billion years. So I have this worry that we are losing some physical content of these models if we are throwing out this information. And the same happens in the quantum case. And this seems to me worrisome. Like by using these relational strategies, it seems to me that we are throwing away this physically meaningful content of our models.
For how I understand the situation in your worry, again, there are two levels. One is purely psychological. We are used to work with the coordinates, we're used to work with the manifold, with that type of picture in mind. And we are not used, and we don't know how to do it in general, to just totally get rid of that. I mentioned that. We don't have a formulation on relativistic physics that doesn't use the manifold, the directions, and so on. So lacking that, we always feel on very shaky grounds when we try to have a description that is purely relational. But we will get used to it. The more substantial worry is that, as I also mentioned, GR is not in general deparameterizable. There's no, because of what I just said, there's no fully relational formulation in terms of some material frame, except the simple models. The more realistic situation will be something in which you have a collection of physical frames, and you can partially deparameterize with respect to one. You can partially deparameterize in some approximation for certain ranges in time or space with respect to one, with respect to the other, and so on. And we understand the transition from one to the other. That is, we will have to develop and use for physics the physical counterpart of what in fact we do with coordinates. There's no global coordinate frame in a generic manifold, on a generic geometry. What do? We have an atlas. We have various charts of coordinate frames, and we understand the transition. So even in the idealized case in which our physical frames behave like coordinate frames, we have to use a number of them with their own approximate validity. And at the quantum level is going to be worse, but that's the classical story. So I don't think it's not that we miss any physics if we go purely relational. We miss physics if we go relational only in simplified models, because of course there's not the full story, and we have to learn to go beyond that. That's my.
Thank you very much for your talk. So my question may seem a little bit simplistic because I'm not a physicist, or I study ancient philosophy, so I don't understand everything. And my question is about tetrahedras that made an echo to me to Plato's cosmology. And my question is, why do scientists choose this geometrical shape to cut the space, as I understand? Why not another one? Yeah. And is there a reason, like a final cause to it, or is it just because it's comfortable, and why it is comfortable?
Okay, there is a technical reason why you go for a tetrahedra, which is that any lattice, any cellular lattice can be triangulated. can be chopped in tetrahedra or at higher dimensions, 4 simplices and so on, and not vice versa. So if you only have an hypercubic lattice, like you use in lattice gauge theory, you add a bunch of diagonal edges and you have tetrahedra, not the other way around. If you have a simplicial lattice, you cannot use cubes to rewrite it. So that's the mathematical thing. So the simplicial lattice are sort of the most general type of structures you can use. Having said that, there is a mathematical convenience, but for effective hydrodynamic coarse-grained physics, you also don't expect that the precise shape, fictitious shape of your atoms of space will matter so much. Most of the quantities should satisfy some degree of universality.
Sorry? We can't hear you actually.
A simplicial lattice is the gluing of simplices. A 3-simplex is a tetrahedron, and then you can do things in 2 dimensions is a triangle. A simplicial 2-dimensional lattice is a bunch of triangles glued to one another. In 3D is a bunch of tetrahedra. In 4D, they are called 4 simplices and so on. That's it.
Okay, so we had 2 more questions, but I guess you want to ask them during the break? Okay, because we are late. So thank you again, Daniele.